All right, my name's Alex,
And my name's Troy.
and this is our final project. What we did was take a sine wave at 130 hertz and put different types of distortion on it. Then we went in Raven and figured out like what the distortion was actually doing to the sine wave. And the sine wave is at it's, as you know, it's a pure tone and it's the fundamental only. So when we're looking at these graphs, we're only seeing a normal sine wave is just this. All this stuff is not here. So what distortion is doing is adding harmonics to it. So what we figured out is that different types of distortion added different types of different harmonics to the sound.
The first one here we'll show you is T-tube, which is short for teletube.
Sounds like that. Sounds great.
When you look at the spectrum here, not just the initial fundamental is shown like a sine wave. Like Alex said, all the harmonics are added. In the teletube, all 12 are present.
And for the next one, we did phase. So it's a phase distortion. This is also showing all of the harmonics. There's certain distortions that show the odd harmonics and the even harmonics. This is showing every single one of them. So with this, the fundamental, it's going by 130 every single harmonic. This is what the phase sounds like. Sounds similar to the teletube.
Again, in both of those sounds, all the harmonics are present.
And you can kind of hear how the teletube sounds brighter. As you can see, the teletube, the higher harmonics in the teletube have a higher amplitude than the higher harmonics in here.
And if you also look at the general shape of the phase, it slopes off faster than the teletube. The teletube kind of, or I had that backwards, sorry. The teletube attacks, goes down slower while the phase will go up and then has its sharper decrease.
Yeah, and that's why it sounds more muted because you're getting the lower frequencies here and the higher frequencies don't have as much amplitude.
The next ones we'll show you will have the odd harmonics. The first one is the drive.
So this is what the drive looks like. I'll show you what it sounds like. Sounds great. This is the program we use to add the different types of distortion. This is the distortion that we used. So what I'm doing is, if this is what the sine wave originally looked like, I'm pushing the drive on it to make it more and more distorted. So that's what you just heard.
When you're looking at the spectrum of the drive 40, you can see that there are formants present. After looking and calculating all the stuff, the drive 40 showed all the odd harmonics. And we also looked at the frequency at the middle of the formants, and those were about double of each other. Say the first one's at 5,000, 10,000, 15,000 hertz.
So the next one, this is what the drive looks like up close. So like when we were talking about the odd harmonics, this is 130. This would be the odd, even, odd, even, odd. So all these higher harmonics are the odds.
The other odd one was the Bronner tube. It also had the odd harmonics present, and this is what it sounded like.
compared to the drive, you can hear that the drive sounds a little bit brighter once again. That's just because the Bronner cuts down really fast. As you can see, the lower harmonics are higher than the higher harmonics. The drive sounds brighter because the higher harmonics have more amplitude than the higher harmonics of the Bronner.
The next ones we'll show you, starting with the C-tube.
Let's do the C-tube. This one's a little weird. You can see that it has formants, but when we try to calculate, when we try to find a pattern in the harmonics, it seemed to be pretty random. Like there wasn't every odd, and it wasn't every
even.
It was
it went from the first harmonic to the 26th to the 45th to the 60th. There's no distinct pattern in between the two. There's no going by odds or evens or fives or 15s, or there's no factor to go in between each harmonic. It was totally random.
And this is what it sounds like. And C-tube stands for classic tube distortion. So that is that's the type of distortion that they used to use back when they first started coming out with distortion, when they first started adding distortion to different sounds.
So that would come back to the Moog thing, right?
Yep. Back to the Moog synthesizers.
The other random one, or sorry, not the random one, was the Bit Crusher. And the Bit Crusher looks oddly similar to the graphs we had seen earlier in class, the saw wave. And if you look at that, the harmonics on the Bit Crusher started with the initial fundamental of 130, and then the second big spike was the 16th harmonic, and then the one next to it was 18th, and then so on was a big change from there's 15 and then 2, 15 and 2, 15 and 2, and that was the pattern within the Bit Crusher.
So every pair is going up by 15 harmonics. Where is it?
Up one, there you go. Down one.
Am I just not seeing it?
I brought it to you. You were just on it.
Oh, we're doing a
Bit Crusher.
Bit Crusher. Where'd it go?
Just grew legs.
Oh,
right
here it is. All right, this is what it sounds like. You can hear all those higher harmonics. It's almost ear piercing. It's completely different from the original sound of the sine wave, which was just the lower fundamental. And it was so high because, I mean, look at these harmonics. They're going up, like they're slowly raising as compared to the other ones where the higher harmonics were slowly decreasing.
And there is a definite pattern to this one. This one is not random. And again, it looks like the saw wave we had seen earlier in class. The last one we'll show you is the amplitude distortion.
Now this type of distortion, all I did in Logic was bump up this volume until it clipped. That means that the audio that's coming in is topping out. You see this 1.5? That's because it's 1.5 over and it's in the red. So it sounds like garbage. That's not what it's supposed to sound like. So
it's what happens when your speakers are it's turned up so loud. You get that feedback noise, and then you have to turn down your loudness, your volume, so you can actually hear what's going on.
And I know everyone has done that at some point, bumping music in the car too loud, and then it starts to distort and doesn't sound good. That's because you're bumping the volume too loud, and you have to turn it down.
Now, initially, to the first 11 harmonics, it was only showing the odds, and then after that, it was every harmonic. And
it just like, here's the fundamental way up here. It It just doesn't look good compared to the other ones.
It doesn't look good and it doesn't sound good.
Yeah, let's play him the sample of the amplitude distortion. I mean, it's just the point of adding distortion is that it's to make it sound good. It's supposed to make the distortion sound good. But when you're overdriving it and it's going in the red, it's gonna over distort and it's not gonna sound good. So when you are recording music, you do not want amplitude distortion. You want to use one of these other distortions as an effect on the sound to make it sound better, not worse. That's about it. That's a project.
That's a project of distorting the sine wave. Thank you.